Welcome back. We are now to Newton's method. This is section 4.8. And Newton's method is something Sir Isaac Newton came up with, one of the applications of his derivative that he came up with. And the idea is, what if we want to know the root or the zero of a function that we can't directly get to? So we don't have direct access to that root. And there's lots of functions that fall into that, lots of nonlinear functions that fall into that category. And what we're going to do is we're going to use this method to approximate where the graph crosses the x-axis. And here's the idea. We have a function. We're going to pick our first choice. That's going to be our x sub 1. We're going to find the y value to that and then come up with the tangent line at that point, which is what this is. And that's going to go down and hit the x-axis, and this becomes our new x value. So we're going to create the equation of a line, and we're going to work backwards to get to the 0. And then we're going to use that one to come up with, and that's this one here, the second iteration. So here's our next one. We're going to go up here and come up with the slope of that tangent line. Which is here in this case. And you can see each attempt, here's what I'm trying to find. This value right here. And you can see my first attempt is quite far away. My second attempt is closer. My third attempt is really close. And the idea is that we just keep doing that over and over and over again. And they even have here a fourth tangent, in which this case, it's getting completely blurred as to where is the point that we're actually looking for. So let's formalize this a bit. And we're going to have y minus, this is basically our point slope form, where our slope is y prime. And our goal is to make it y equals 0, right? We're hitting the x-axis, which is where y equals 0. And we end up with this for our first iteration. We know our first point. This is f of x sub 1, and this is f prime of x sub 1, And we're going to formalize this into x sub n plus 1 is going to equal x sub n minus f of x sub n over f prime of x sub n. Which means we can just keep doing this process over and over and over again until we get closer and closer. Now, this all depends on us getting a good guess. So if a good guess is not given to you at the beginning, then what you can do is graph it in a graphing calculator and then use that to get a good idea of what a good guess would be. Now, in real life, you might already have a good guess of what it might be based on where your function even came from. All right, so what we're going to do just real quick here before we get into an actual real example is we're going to draw in a couple of iterations without actually knowing what the numbers are. So our first guess is going to be there, and we want the tangent line right at that point. It's going to be there. And that's going to hit here, which is going to be our x, that says x0. I'll call that x1. This will be x2. And then that's going to go up to here. And now we're going to come up with our next guess. And we're looking for this root here, apparently. And our tangent line is going to look like that. And you can see that is very, very, very close to our goal, which is this point right here. So you can see it's very, very close, even just after a couple of iterations. In fact, in one of our examples that we're going to be doing for this video, after one iteration, we've already hit our goal. So let's move on to a couple of examples. And I'm going to teach you some stuff with your calculator here. So we have our first guess is going to be x sub 1 equals 2. And we're going to find the third approximation, that's x sub 3, of this function here. So let's start with our function. And we'll need the derivative function for this as well. And here's what I'm going to do. I'm going to load this into y sub 1 and this one into y sub 2 in my graphing calculator. So I'm going to have x cubed. And I have to hit the right button for mine to get out of the exponent. You might have to do that as well. Minus 2x minus 5. And y sub 2 is going to be here, 3x squared minus 2. So make sure you load that in. And I'm going to start with my first one. I'm going to have 2, and I'm going to use a memory here. I'm going to use the store button. That's above my on button for this particular type of calculator. And I'm going to store this into A. So I'm going to hit alpha A. And that's a memory. So now in A, I've stored the number 2. So I'm now going to use the algorithm. I'm going to do A minus y sub 1 evaluated at A. Make sure you close the parenthesis. Divided by y sub 2 is my derivative function. Y sub 2 evaluated at A. And I'm going to store that off as my new A. It's going to update my A. So here's what's going to happen. I'm going to hit enter. And I'm going to end up with x sub 1 was 2. X sub 2 is 2.1. And now all I have to do is just hit enter again. And it's going to take the updated A that I just updated, plug it into there, and redo the process. So I'm going to hit enter again. And I'm going to have to round this off, 2.094568. And this is all that this particular problem is looking for. But if I just keep hitting enter, it's going to get closer and closer and closer. And you can see it's now identical. So this was the third, the fourth, and the fifth are now identical to this many decimal places. So it's a really efficient way of doing this. We're going to do one more here. And we have x sub 1 is going to be 2. It just happens to be 2 again. You don't always pick 2, of course. You're going to pick something that's appropriate. And we have our function y equals 2 over x minus x squared plus 1. This is going to be, I'm going to store that into y sub 1. And my derivative function is going to be negative 2 over x squared minus 2x. This is going to be my y sub 2. So let's go back into here. I'm going to clear that and clear that. So I'm going to have 2 divided by x minus x squared plus 1. And for my derivative function, I'm going to have negative 2 divided by x squared minus 2x. And I'm going to quit out of that. And once again, I'm going to store 2. I'm going to store that. Again, that's above the on button. Mine's a little, I've been used a little too much. Store into alpha A. And now I'm going to use the algorithm. And again, the algorithm that I'm using, just as a reminder, is here. This one here. So there's my y sub 1 at A. This is my y sub 2 at A. So here we go. I'm going to do A minus y sub 1 evaluated at A. Again, make sure you close your parentheses. It won't work if you don't close your parentheses. Divided by y sub 2 at A. And I'm going to store that off as my new A, my new updated A. And you'll notice my third iteration is a little bit different. So x sub 1 was 2. X sub 2 was 1.5 bar. And x sub 3 was 1.5215. We'll round it off there. So that's an approximation. And again, we could just keep going to get it closer and closer and more refined as we do it. And you can see by the 5th or 6th iteration, it's identical. And that's Newton's method. Now I kind of taught this in a cheat method where we're using the calculator to do all the work. You could try to do it by hand, but it's going to be quite a bit more work. I hope that helped.